Carbon is one of the simplest of all the elements. At element number 6 on the periodic table, it's relatively small in size. But this little element holds a crucial place in the workings of the universe and particularly of life. Most of us are familiar with the term organic as it's used colloquially to describe naturally grown foods or other products. The retail market has adopted the term to essentially mean natural or made with natural ingredients. But chemists use the word organic in a very different way. The term originated in the 1700s and was used to refer to the material that was sourced from organisms. You see, the very early stages of study of modern chemistry and biology, we realized that everything in the universe is made up of atoms and molecules, and that includes us. But there are many compounds that were extracted from living things that chemists simply weren't able to find anywhere else. Compounds like urea and butyric acid. Based on this observation, it was generally accepted that organisms possessed a special characteristic called vitality. It was this vital energy that gave them the ability to make these sorts of compounds. But in 1828, a young German researcher by the name of Friedrich Wöhler changed the way we think about the chemistry of living systems. In what can only be described as a happy accident, Wöhler was trying to create a compound called ammonium cyanate from ammonia and cyanic acid, both inorganic compounds themselves. But something went wrong with his reaction. Something went wonderfully wrong, and he instead created urea. Now, this observation led Wöhler to only one possible conclusion: that vitalism was an incorrect theory. These so-called organic molecules could be made without the aid of a living thing. Our way of thinking was forever changed, but the name organic stuck, and we now use the term not to refer to molecules made by living things, but to refer to molecules with carbon-based structures. Because it was realized that compounds like urea could be made in a beaker without the assistance of an organism, chemists started down the path of learning how to create, manipulate, and modify carbon-containing compounds. With the paradigm shattered, the path was open for humanity to discover how to create biologically active molecules like antibiotics, sugar substitutes, and even custom-tailored biopolymers like DNA and enzymes. Now, these can be used to modify the chemistry of living organisms. But we're getting ahead of ourselves. Before we can get to all of those materials, we have to answer the question: why carbon? What makes this element so very special that life has chosen it as the centerpiece for the most fundamental molecules of life? Let's begin by taking a look at carbon and asking the question, why is it that carbon is used as a backbone or scaffold of so many molecules that drive living systems? What makes carbon so special? The answer is threefold. First, carbon is relatively abundant. It's difficult to estimate exactly how much carbon is available at or near the surface of the Earth, but what's undeniable is that it is concentrated there. Now, the second is stability. As we saw back in our bonding lecture, carbon bonds to itself with relatively high strength, requiring about 400 kilojoules of energy to break a mole of those bonds. That's more energy than most bonds would need in order to break. What this means is that carbon skeletons are sturdy. They can act like the frame of a car or a building, standing rigidly and supporting other structures that can undergo reactions to perform their functions. Finally, there's the issue of complexity. To create a biosphere with such tremendous diversity, Mother Nature needed a large library of compounds. The first step to increasing the variety of chemistry out there is to choose a scaffold system that has great variety in the shapes and sizes that it can have. Carbon is perfectly suited for this because its 1s2, 2s2, 2p2 electron configuration allows it to make up to 4 bonds in a tetrahedral arrangement. And you may recall from our molecular geometry discussion that it was only when we had 4 electron domains that our geometry started to become non-planar, that is, 3-dimensional. And because of this, chains of carbon can extend, branch, and even fold back on themselves. And in doing so, they create enormously complex structures, all of which have even more unsatisfied bonds to which a variety of atoms can be attached. When you compare these three properties of carbon, its abundance, stability when bonded to itself, and its ability to form complex chains of atoms, nothing else on the periodic table can compete. Among the elements, just a few have the abundance to even be considered to serve as a molecular scaffold. Among the few elements abundant enough to be in the running, none can beat carbon in the necessary categories. Hydrogen offers a powerful single bond to itself, just like carbon, but it lacks the ability to make any additional bonds to provide the needed complexity to serve in this role. Abundant nitrogen and even the tantalizing possibility of silicon-based life are very unlikely, since both can form complex scaffolds in theory, but a quick look at their bond enthalpies shows that they lack the stability to serve as that scaffold. In short, if silicon-based life exists, it will have a drastically different chemistry than we have come to associate with living systems, since scaffolds made of this element would simply be too fragile. It's clear that carbon-based molecules offer more variety, stability, and functionality than any other possibility. Now, another element that we'll see again and again in our discussion of organic chemistry is hydrogen. The most abundant element in the universe, hydrogen fell short in our test for a good backbone element because it can only form one bond to complete its valence electron shell. So hydrogen would be a lousy backbone choice, but its ability to make only one bond does have a use. Hydrogen atoms bond strongly to carbon, but only to one carbon. This makes a carbon-hydrogen bond a perfect way to terminate a chain of carbon atoms. So hydrogen behaves much like a placeholder in this respect. When we combine just these two elements, hydrogen and carbon, we get a class of compounds called hydrocarbons. Most of us are familiar with hydrocarbons from their role in fuels. They're the principal component of a number of motor fuels, from natural gas to gasoline to kerosene. All of these vital products consist of very little more than hydrogen and carbon. But hydrocarbons have many other uses. Benzene finds use as an industrial solvent. The gas ethylene is used in plants to signal that it's time for fruit to ripen. And this little molecule, called cyclopropane, found use in the mid-1900s as a surgical anesthetic. So hydrocarbons themselves, though representing just a small slice of carbon-based molecules, have a very rich and complex chemistry all their own. So for this lecture, we're going to stick to understanding this simple class of organic compounds. Don't think there's enough variety there to fill a lecture? Let's test that theory. My goal now is to convince you of how complex hydrocarbon structures can really become. And because I'm going to draw some fairly complex structures, I'm going to use a type of notation that we haven't seen yet. And that is, I'm going to use what's known as a skeletal formula. And this is what a skeletal formula is. Now, at the ends, each of these represents a carbon atom. And every kink in my line here also represents a carbon atom. So here I've got, for example, a hydrocarbon with 1, 2, 3, 4 carbons completely saturated with hydrogens. And again, here is a molecule with 1, 2, 3, 4 carbons, all saturated with hydrogens. Now, when I do this with relatively simple small hydrocarbons, I get just a few possibilities. Here is the total exhaustive list of possible what we call saturated hydrocarbons, that is, those that have only single bonds, that contain 4 carbons. There are 2 potential isomers. Pretty simple, right? Okay, let's move up a step here. Let's look at 5 carbons. In the case of having 5 carbons, there are actually 3 different ways to connect those 5 carbons together into geometrically distinct configurations, or isomers. Not too bad, we can still keep track of that. Let's take another step forward. Let's go up to 6 carbons. Oh, now we have 5 isomers. Now we're probably starting to notice a trend here, right? Let's go one more. Let's consider 7 carbons. How many different ways can you put 7 carbon atoms together into either a chain or a branched structure? Well, the answer is you can do this 9 different ways. So now it should start to sink in a little bit. As we add additional carbon atoms, we increase the potential variety, and it's not a linear increase either. It's taking off really quickly here. But this is just the beginning. Consider this. This is a plot of all the potential numbers of isomers of hydrocarbons that contain up to 21 carbon atoms. Now, I've had to break this into 3 different plots, and the reason is, if you look carefully at my vertical axes here, our first 8, we end up with a grand total here at 8 of 17 potential isomers. This is octane. But when I jump up just a few more and I go to 14, 15, or 16, these columns are so gigantic that all of these columns would appear essentially flat, right? Because we're getting a sort of an exponential response here. And if we continue, we go beyond 16 and go all the way up to 21, look at the number of possibilities that I'm dealing with here. We're dealing with possibilities that are approaching the millions. And that's just with 21 carbon atoms. This is a very reasonable size here. So molecules like octane from gasoline, cetane from diesel fuel, and a 21 carbon atom, which would be called henicosane, when you put them all together, creates a library of well over 1 million hydrocarbon structures. And that was handicapping myself to having only single bonds within it. Right? Now imagine cyclic structures. Right? Imagine double bonds and triple bonds. Things can get really, really complicated really, really fast. So, now that we've decided to dedicate our lecture to hydrocarbons, let's be sure that we can discuss them without any confusion. That might be a bit tricky, though, since we just realized that there are quite literally millions upon millions of unique molecular structures that we have to potentially consider. Learning a common name for each would be sort of like trying to memorize the New York City phone book. It just isn't going to happen in a reasonable amount of time. Luckily, we have a much more manageable way to talk about hydrocarbons, courtesy of the International Union of Pure and Applied Chemistry, also known as IUPAC. IUPAC oversees and recommends naming conventions so that instead of having to memorize millions of unique names, we can instead memorize just a few simple rules that are used to construct those names. Let's begin our inquiry into how to name saturated hydrocarbons by thinking just about the number of carbons in the molecule. So we'll do some very simple hydrocarbons here. Now, when we look at this, we first see methane, ethane, propane, and butane as names for hydrocarbons that contain 1, 2, 3, and 4 carbon atoms, respectively. These prefixes come from generally historical names, historical sources. They're not really terribly methodical. Fortunately, before too long, scientists came a bit to their senses. And as we begin adding more and more carbons beyond 4, we see things like pentane with 5, or hexane having 6, heptane with 7 carbons, octane with 8, nonane with 9, and of course decane with 10. And this trend continues using the appropriate prefix for the appropriate number of carbons. But this system of naming is incomplete. It only allows us to determine how many carbon atoms are within the molecules. And as we now know, there is a tremendous amount of variety, especially in some of these later molecules here, in terms of isomerism. So although this nomenclature system gets us started on distinguishing what kind of hydrocarbon we're talking about, it doesn't complete the picture. Now, to complete the picture, we've got to think a little bit more about how these molecules can branch. In the case of propane, there really isn't any branching at all to worry about. You can't have a branch with just 3 atoms. The skeletal structure of propane will always look this way, no matter what. But notice that in this case, I've labeled this molecule N-butane. The italicized N at the beginning stands for normal. And normal is our generic nomenclature term that lets us know that all the carbons are in one continuous straight chain. So this would be an example of the skeletal structure of N-butane. However, consider this. You can branch a butane molecule. It can look like this. So we need a new name that allows people who are reading whatever it is that we happen to be writing or listening to whatever we happen to be saying to know which one of these 2 isomers we're talking about. So we call this particular structure isobutane. Okay, great. So we have 2 common names for the 2 potential isomers of butane. No problem there. Let's keep going. How about pentane? Well, remember, pentane can branch in several different ways. It can branch like this with one carbon in the branch, giving us what we would call isopentane. Or it can be even more highly branched, creating a structure that's known as neopentane. So you can see we're about to run into a problem, aren't we? As we go on in the number of carbons, we're going to start running out of prefixes to use, or at the very least, the mental capacity to memorize all of them. We certainly couldn't memorize over 1 million potential names for 1 million potential hydrocarbons from 1 to 21 carbons. So we use a different system when it comes to naming hydrocarbons to be a little bit simpler on ourselves, and that is the IUPAC nomenclature system. Now, in the IUPAC nomenclature system for saturated hydrocarbons, it's actually fairly simple. We just follow 4 rules. The first of which is this: identify the parent hydrocarbon, which is to say find the longest string of carbon atoms that you possibly can. The second thing we do is catalog all of the alkyl substituents that are on those particular parent hydrocarbon molecules: methyls, ethyls, propyls, etc. The next thing we need to do is assign a numerical address along that parent hydrocarbon so that we can indicate the locations of all of those substituents that we identified in step 2. And finally, we construct the name using a set of simple rules. And we'll show you exactly how to do this. Let's take a look at those molecules we looked at previously. Here's our molecule of, the common name rather, of isobutane, isopentane, and neopentane. Now let's assign IUPAC names to them instead. Take a look at isobutane. How many carbons in the longest chain? Of course, there are 3, right? The longest chain we can find is right here. 1, 2, 3. The next question, what are the substituents? Well, there's 1 carbon off the chain. Because the prefix for 1 carbon is meth, we will call this a methyl substituent. Now, in the case of isobutane, there's no need for an address because there's only 1 potential location for that split to be. But notice that isobutane, by common nomenclature, is actually methylpropane in IUPAC nomenclature, because common nomenclature considers the total number of carbon atoms in the name, whereas IUPAC considers only the length of the parent chain when it comes to the root of the name. This means that isopentane is actually going to be called methylbutane. This means that neopentane would be called dimethylpropane, because the longest carbon chain is only 3 atoms, and there are 2 methyl substituents. Now that's all well and good so far. We haven't had to worry about where the substituents were on the parent chain, because the parent chain was so small, there was only 1 potential location. But there are potential situations in which that's not true. Take a look at this molecule right here. Let's say we want to name this molecule using IUPAC convention. How are we going to accomplish that? Well, we have to define the parent hydrocarbon and the substituents. And here we are. I've highlighted the parent hydrocarbon in blue. I've highlighted the 1 methyl substituent that I found in orange. So now I'm ready to begin naming this. But before I can finish my naming, I've got to know exactly where the methyl group is. Now let me assign my numerical address to my parent hydrocarbon. So here they are. I've started with a 1 at one end of the molecule. I've chosen the right end, going along sequentially until I reach 7 at the far end. But there's a problem with this. The IUPAC nomenclature system requires that I give the lowest possible address number to my substituents. In this case, I've given the methyl group a 6. But if I were to number this chain the other direction, my methyl group would receive a number of 2. So in this case, this is the appropriate numbering system for the parent hydrocarbon. A methyl group at position 2 on a 7-carbon chain is 2-methylheptane. Let's try a few more. Let's take a look at this molecule. Well, of course, we can define our parent hydrocarbon as the longest chain and a methyl group. This is also a methylheptane, but it's clearly not the same molecule. And IUPAC allows us to demonstrate that, because when we give this particular chain a numbering address system, we find the methyl group appears at position 4, not position 2. So this is 4-methylheptane. It's a distinct compound, therefore it has a distinct IUPAC name. Just try a couple more here. Here's yet another one. 7 carbons in the parent chain, but now I've changed my substituent identity, right? This has 2 carbons, which means that that's an ethyl substituent. This is 4-ethylheptane. Another, here we go. Here's one where my parent hydrocarbon is also 7 as before, but now I've got 3 methyl groups. So now I have to convey the fact that there are 3 methyl groups and also the individual address of each one. So, using my naming system, I would get 2,4,6-trimethylheptane. Just a couple more here. Here's one where the carbon chain is a different length. Right? In this case, it looks like I've got 8 carbons in my chain. So although it may look very similar to my original example over here, remember the parent hydrocarbon's bigger. So in this case, I'm looking at 2-methyloctane because the parent chain is longer. And in this case, I have multiple substituents now, methyl and ethyl substituents. So when I, again, locate my parent hydrocarbon, I find 2 methyl groups and an ethyl group. And when I apply my numbering system as before, I get 6-ethyl 2,4-dimethyloctane. And I want you to notice that I've alphabetized based upon the E from ethyl and the M from methyl, not the D from dimethyl. This is also by convention. Right? So this should give you all of the information you need to name just about any simple saturated hydrocarbon that you might encounter. So we've seen how, although compositionally very similar, hydrocarbons can be structurally very, very diverse. Diverse though they are, they also share quite a few properties in common. For example, nearly all small hydrocarbons are combustible. From the natural gas or propane in your barbecue grill, to the octane or diesel in your car, to the kerosene used in home heating. All of these compounds can burn readily when mixed properly with atmospheric oxygen. Natural gas consists primarily of methane and is valued for its clean burning properties. Notice that 1 mole of methane creates only 1 mole of environmental carbon dioxide on combustion. This is an attractive property of methane, but at ordinary temperatures and pressures, methane is a gas, which means that it has to be compressed into a liquid if it's going to be carried on a vehicle or another machine, a potentially hazardous and expensive proposition. Diesel fuel, on the other hand, suffers from the exact opposite problem. The fuel itself is very stubborn to vaporize, requiring high engine temperatures to function correctly, and sometimes even freezing in extreme cold. This is evidenced by the tendency of drivers of these vehicles to leave their engines running when jumping out to make a delivery or perform any quick task outside their vehicle. Now, the reasons for these differences in physical properties of hydrocarbons is tied to their structure and the intermolecular interactions that they produce. Of course, we can deduce that larger hydrocarbon molecules should form stronger dispersion forces with other molecules of the same type. So it should come as no surprise that methane has a much lower boiling point than octane, which boils at a lower temperature than cetane, and so on. But the overall size of a hydrocarbon isn't all that matters when it comes to its phase behavior. Remember that a vast number of structural isomers can form in even modestly sized hydrocarbons. And each of these hydrocarbon isomers will have its own distinct shape, which will play a role in how it boils. To better understand why hydrocarbons span such a wide range of boiling points, first consider a few examples from the macroscopic world. Think about stacking lumber. When you place the boards one on top of the other, there's very little empty space. Most of that surface area on the boards that you're stacking is in contact. Now think about a container full of basketballs. No matter how carefully you might try to arrange them, there will always be empty space. This means that a much smaller surface area will be making contact among those objects. Now, with this in mind, now consider 2 simple hydrocarbons, butane and isobutane. Now, the effect of the branching on isobutane is to create a more globular-shaped molecule than N-butane itself, reducing the ability of each molecule to make a productive contact and form dispersion forces. Compare their boiling points, and this makes sense. N-butane boils at just about 0 degrees centigrade, while isobutane boils nearly 12 degrees centigrade lower than that. Combine the effects of size and branching, it explains why methane and propane are gases which have to be compressed for use, why isobutane is added to some butane fuels intended for outdoor camping to ensure that it vaporizes well, and also why diesel fuel can be so problematic in extremely cold environments. But these properties aren't just a factor in how these hydrocarbons are used. they're also a key factor in how they're collected. Practically every hydrocarbon molecule that you have ever used started off as part of a crude oil mixture. Crude oil, or petroleum, is a naturally occurring mixture of hydrocarbons of all shapes and sizes, formed as biological materials, usually bacteria, decay slowly underground, where there's no oxygen to convert them into carbon dioxide, water, and other decomposition products that we typically see in decaying biomasses here on the surface. Ancient peoples discovered some of these deposits of thick, viscous, tacky black material. And there's evidence that as early as 5000 BC, some cultures had collected and used it as a waterproofing agent in boating applications. But there was a different kind of material hiding in that tar, one that was made from smaller hydrocarbon molecules, one that was a clean, easy-pouring liquid that burned evenly and brightly. This tar was called bitumen, and the mystery guest hidden inside was discovered in the Middle East about 1,000 years ago, where records show that it was obtained by heating bitumen in a jar, then collecting the resulting vapor in a separate container by condensing it on a cool surface. The result was a cleaner, more well-behaved liquid that could be used as a solvent or fuel. Modern techniques for isolating one hydrocarbon from another aren't that much different than those used by the Babylonians 1,000 years ago. We call the modern technique cracking or distillation, and it works on the same principle as that Babylonian system did. A sample of crude oil is pumped into a heated column containing a series of plates, each with an opening to allow vapor to pass through. When heating the sample, components of higher volatility reach the vapor phase more easily and can ascend the column more quickly. Components of moderate volatility tend to recondense as they ascend the column into cooler regions, and some components of extremely low volatility never get out at all. The end result of this is a vertical column along which hydrocarbons are separated in space based upon their boiling points. Low molecular weight, highly flammable materials like natural gas and gasoline are found near the top, while the high molecular weight, less flammable materials like bitumen used for road tar are found near the bottom. If you want to collect gasoline, diesel, or kerosene, you simply need to tap the column at the right location. We call these separated samples fractions, and the technique that I just described, fractional distillation. And once my hydrocarbons have been distilled to a suitable purity, I'm ready to use them as solvents, fuels, or even starting materials in chemical synthesis. So let's sum up. We started this lecture by trying to define organic chemistry. We saw how the origin of the name is based on the flawed concept of vitalism, and how the name has changed from referring to biological molecules to referring to molecules based on carbon backbones. Then we tried to understand why carbon-based molecules offer the most stability and variety of molecular scaffolds, using an element abundant enough to play this key role. Then we dove into organic chemistry by exploring hydrocarbons. We discussed the origins of some of the names given to simpler hydrocarbons, and how the immense library of possible compounds that can be made from just a few atoms quickly caused scientists to adopt a more uniform nomenclature system, the IUPAC system. Then we considered a few properties of hydrocarbons. We saw that they are almost uniformly combustible and insoluble in water, but how their volatility in particular can vary dramatically. Finally, we talked about how chemists and engineers can exploit the differences in volatility of hydrocarbons to separate them from one another, using a modern version of the ancient technique of distillation. Next time, we're going to take our hydrocarbons to the next level by removing a few of those place-holding hydrogen atoms and replacing them with new elements and groups of elements to create compounds with all new properties.